Okay, then we move on to the next part. Okay, properties of Ors estimators. 3 properties. You learn all of them in your undergraduate years. Okay. First one, the sum and mean of residual is 0. Okay, it makes sense. Remember, we want the residuals to have a random distribution, sometimes negative, sometimes positive, so that the sum and the average will be 0. Covariance between x and residual 0, no relationship between x and residuals. It is just like what happened in the population regression function. Ideally, we want no relationship between x and u, the disturbance terms or error terms. Last one, for the sample regression function, the sample mean of x and sample mean of y lie on the regression line. Okay, so in equation terms, this is what each property means. Okay, but I think if you answer with, I expect you to answer with the written explanation. Okay, but don't get confused between this question, properties of OAS statistics or estimators, and the next important question about the assumptions of the regression model. So don't get confused between the 2 types of questions. Over the years, I've noticed when I mark the bootcamp test, students get confused between the 2 questions. Okay. Goodness of fit R square, you already learned it at undergraduate year. Explain sum of square ESS, but Woodridge would rather call it SSE. This is the equation, just to refresh your memory. R square is explain sum of square divided by total sum of square. And then total sum of square is called TSS in Gujarati, but it is now called SST, okay, in Woodridge. And this is the equation. I'm not going to ask you to do these calculations, but I think I will give you SSE, SST, and so forth. Then you have to calculate the R square and interpret the R square. And then lastly, residual sum of square RSS. It is now called SSR, okay, in Woodridge. It's about the difference between actual y and y hat. You take the square, then you add up all the answers. And then you already learned at undergraduate level, R square is range between 0 and 1. And you also learn one weird characteristics of R square. It keeps increasing as long as we add more and more explanatory variables, regardless of whether they are relevant or not. This is why it is better to use adjusted R square to compare the goodness of fit of regressions with different numbers of explanatory variables. So for the first 2, they have the same number of explanatory variables. First one, marks explained by study hours, party hours, lecture attendance. I think all 3 are relevant explanatory variables. So that explains the R square or goodness of fit is quite high. Second, regressions marks explained by tutorial attendance, but we have got 2 irrelevant explanatory variables, number of dogs and size of the bathtub. So I commit seriously overfitting. So that explains why the R square or the goodness of fit is so low. Finally, the last one, but you see more explanatory variables compared with the first 2. Remember, the first 2 have got 3 explanatory variables, but for this one, we have 5 explanatory variables. So it already implies it is not possible to compare the third regression with the first 2, because R square is guaranteed to be the highest for the third regression due to these weird characteristics of R square. Okay, 0.93, but you can't compare with the R square of the first 2 regressions. But if we just use our theoretical thinking, marks explained by study hours, lecture attendance, tutorial attendance, whether you have a WhatsApp study group. So the first 4 explanatory variables make sense, but the last one is irrelevant, number of cats. Okay, but I think we better use adjusted R square, okay, to compare the goodness of fit of regressions with different number of explanatory variables. Okay, and then different functional forms, I will go through it very quickly, okay, because you learned it in your Eco 242. So we will do question 4, in-class exercise question 4, although you already have the answer. Okay, we will focus on the simplest linear model, double log model, log lin, and lin log. 4.1 and 4.2 linear function, quite straightforward, so I'm not going to go through the explanation. Maybe I stop for 15 seconds for you to look at the answers on your own. Okay, double log, you take log of x and log of y, and I think the answers are also self-explanatory. Percentage change of x, percentage change of y as a result of 1% change or 1% increase of x. So can I also keep quiet for 15 seconds? I want you to go through the answers on your own. Okay, I rather want to focus on log lean and lean log model. 4.5, 4.6, they are examples of log lean model, meaning I take log of y, but x remains linear. So when you interpret the slope parameter, it is percentage change of y as a result of 1 unit change of x. And then when you interpret the slope parameter, you must multiply by 100. So let's look at this one. Real GDP explained by year, then you have to multiply the slope by 100. So this is the interpretation. When time increases by 1 year, it means the year variable increases by 1 unit or 1 year. The sample regression function predicts that on average, real GDP would increase by, you see, I multiply the slope by 100. It will increase by 2.469%. Okay. 4.6, log of happiness index explained by age. So I have to multiply by 100. Positive slope, it means that when I get older, I become happier. So the interpretation is when age increases by 1 unit or 1 year, the sample regression function predicts that on average, happiness level would increase by 12.34%. Okay, and then the last two are examples of lean log model. This time I take log of x, but y remains linear. And then when I interpret the slope parameter, I have to divide it by 100. Okay, unit change of y as a result of 1% increase of x. So let's look at this one. Real GDP explained by log of money supply. So the interpretation is when x money supply increases by 1%, sample regression function predicts that on average, real GDP would increase by, you see the division, by 100 by 25.848 units or rand. Okay, last one, stress index explained by log of volume of work. So it means the slope parameter means when x volume of work increases by 1%, the sample regression function predicts that on average, the stress level or stress index would increase by, I divide the slope by 100. Increase by how much? 4.6825 units. Okay. Okay, then the next one, it's about the assumptions of the linear regression model. We start with the first five for the they are applicable to the simple linear regression model. You are going to run across more or less the same assumptions when we move on to multiple linear regression in the next chapter. And then I will focus on the study guide explanation. Okay. Okay, 5 assumptions in total. The first one is easiest. The first two are the easiest. Linear in parameters, meaning this is the functional form. So y is related to x and the error term. Okay. Then b0 is the constant and b1 is the slope parameter. Each parameter to the power of 1. Linear in parameters. Okay. And again, I just want to remind you that although y is related to x and u, there is hopefully no relationship, no correlation between x and u. Okay, as I mentioned in the last video. Second one, random sampling. Okay, we collect the data randomly with a random sample. Sample size of n, starting with the first observation, second observation to the nth and the last observation. Third one, there must be variation in the x or the explanatory variables. Okay, so in other words, the x values cannot be all the same, okay, in the full sample. Otherwise, I will only have a vertical line, the so-called regression line, which is strictly speaking not a regression line. The fourth one, we hope this condition would hold, although as I said in the last video, it is unlikely to happen in the bivariate regression or the simple linear regression. Meaning the error term u or the disturbance, which also means the omitted explanatory variables, on average, expected value at each x is 0, constant value 0. The last one, homoskedasticity, I hope the memory is coming back. The error term has a constant variance at all x values. So this is the ideal outcome, constant variance of error term at all x values, homoskedasticity. And this is the bad outcome. This is an example, wage as a function of years of education. You see as the person becomes more educated, you see 16 years, then the variance of error terms increases. You see the difference. It's much narrower at the lower levels of education. And then on a certain page of the prescribed textbook, chapter 2, there is an explanation why there is heteroskedasticity with this wage regression. So let me stop for half a minute for you to go through this explanation paragraph. Okay. And then just to remind you, okay, this one, I run the sample regression function many times, then I derive different B0 head, but on average, the expected value of the B0 head would give me my true B0 from the PRF. And then similarly, I run the sample regression functions many times, collecting different sample each time to derive my B1 head. Then I put all the B1 head graphically. Then on average, the expected value of B1 head would be equal to the true B1. Okay. And then lastly, remember this is the variance of the error terms, but strictly speaking, we would never know this answer because the variance of the error terms comes from population regression function, but we know due to time and budget constraint, we could never interview the full population. We can only interview the sample, so we can only estimate the variance of the error term. So this is why you see the head here, estimated variance of error term. We make use of residual sum of square divided by n minus k minus 1, and since for the simple linear regression or bivariate regression, k is equal to 1 and then 1 constant. Therefore, the denominator is n minus 2. Okay, and we hope that on average, the mean of the estimated variance of error term will give me the true variance of error terms, just like this graphical illustration. Okay. And then the last part, the variance of constant parameter and the variance of the slope parameter. The equations, you don't need to memorize the equations. Okay, they will be given in the formula sheet. Okay, so numerator, that's the variance of the error terms, and then this is n to the power of minus 1. In other words, you actually can put the n here, okay, in the denominator, and this is the total sum of square of x's. Don't get confused between the total sum of square for the r square calculation. So I just want to remind you, this is the total sum of square for the r square calculation. It relates to y, variation of dispersion of the y around the mean y value. Okay, but if I go back to this equation, estimated variance of constant and variance of B0 head and variance of B1 head. Look at the denominator. The total sum of square, it is in connection with x. Do you see the x here? And this is the equation. It actually means the dispersion of x around the mean of x. Okay? And then, remember we want the variance of B0 head and the variance of B1 head to be as small as possible. And, okay, first one, I'm going to ask you, okay, you have to interpret 3 key terms, okay? I think let's start with the first one. When the sample size gets bigger, then the variance of B0 head would decrease, because remember I said you put this n to the denominator. As n increases, then your denominator gets as your n increases, your denominator would get bigger, and then this variance of B0 head would decrease. Okay, and this is the explanation. As the sample size approaches the population size, it means I collect information from more and more people, then the total variation in x would increase. Okay, and if the total variation of x would increase, then this term would also get bigger. So again, the denominator would get bigger. Then the variance of the parameter would become smaller. Okay. I will leave the last 2 explanations in the next video because I'm running out of time.